welcome René Mayrhofer from University JKU Linz and about his presentation about computer science between energy saving and uh, waste. And then I will give the word to you, René, and I will enjoy the presentation.
Thank you. Um, let's see if that works. Now, do do I still? Okay. Maybe I can pin it. Does everybody see it? Okay. Excellent. Then, thanks for having me. I'm René Mayrhofer. I head the Institute of Networks and Security at Johannes Kepler University, and that talk, as already announced, from computer science between energy savings and waste, from video conferencing to blockchain, is a bit of a leftover, you could say, from the time a couple of years ago when we had lots and lots of video conferences. And in the next couple of years, we had lots of discussions of how wasteful is it actually to have video conferencing, to have video streaming, to work from home? What is the energy impact of working from home? And that brought me to maybe try and estimate a little bit. Since I don't have any primary data sources, I don't have any numbers on energy consumption on a global or grid level, most of this talk is based on numbers that others have gathered and numbers and analysis that I've just tried to collect out of curiosity from very many different sources. On many of my slides, you will see the sources at the bottom row. Feel free to click at those primary sources that I used, and those will then refer to other sources of their data. But let's deep dive into what can we find out with reasonable effort on how wasteful really is it to have what we are currently doing right now. So that exactly that change from everybody coming together to the same room, sitting together for a conference, sitting together for a lecture, which has its benefits. But comparing that to this world that we now very often have, where everybody is in front of their own desktop environment and participating actively or not in video presentations and video conferences. Well, maybe occasionally it's not exactly like this. Occasionally it's like that. You only have a small corner in a shared apartment where you can actually try to participate in a meeting, or you sit at one cafe side. And of course, next to it, somebody has other video streams running, and I'm not saying which one that is. But yes, in video conferencing, we compete for your attention with all the other forms of entertainment. And yes, I'm fully aware that most forms of video streams will be much more entertaining than what we can give to you. So I can only hope that I can make it as interesting as possible so that you will take some of the numbers that I tried to pull together away from today. But let's go back to what does it actually mean if we have any such digital communication? Communication is the key for internet services. And to have any form of communication, we require a communication medium. And of course, we require any kind of service on the other side of that communication. And for that communication medium itself, it is possible that we could use dedicated infrastructure for both or multiple communication parties to just use that directly and solely. And some of the biggest internet service companies that we are talking about today, they actually lay their own fiber cables under the ocean so that they have primary and sole access to their communication infrastructure. But for most of us, the likely way to do it is to use infrastructure, publicly available infrastructure that's already there, which basically means the internet. So the all kind of communication that we have today tends to converge into the internet. Of course, the internet is a shared resource and controlled by many parties that we don't necessarily completely trust, which means that any such communication going over the internet creates an attack surface, is ripe for being abused, for being attacked, or just having unintentional mistakes. It can fail. Availability can go wrong by simply somebody misconfiguring a DNS server or a BGP router or whatever. And that has to be distinguished, those mistakes, those unintentional mistakes that are an issue for safety usually, have to be distinguished by intentional attacks, which are a security issue. I will come back to the security concern a bit later after we've seen the first numbers on what the communication itself actually requires. Because any form of digital communication really needs both cables that is very heavy to lay those cables as we do here in Central and Western Europe. We basically dig them in at least a meter underground. It's very wasteful to really have those cables laid in the first place. But once the infrastructure is there, and that doesn't matter much if that's copper or fiber infrastructure, that can stay available for decades. And the first numbers that we have mean that fiber cables, as have been laid like 10 to 20 years ago, don't seem to deteriorate in any measurable form at the moment. So once the cables are there, the infrastructure work, that one-time investment has been done. Of course, in other regions, for example, Asia, closer to the equator where it doesn't freeze all that much, cables are laid in a much easier way, and that's why they can also lay cables much faster and with less effort. But whatever we have in terms of cable infrastructure and how we got there needs power to run. Because there's, even if the fiber cable itself is passive, it needs those optical transceivers on both sides. So let's ask the question, how much power, how much electricity does it actually need to keep these communication lines, to keep those cables running? Or put differently, how bad is it actually? How bad is the internet for the global energy consumption? And we can try to come up with some estimates. And a couple of years ago, I found one blog post here in the bottom right corner that I found reasonably well argued. And while I did not redo the analysis from secondary sources, which of course would be nice, I it seems reasonable. And at the very end, I'll come back to how good are any of those numbers. So in that estimate, that actually traces back to data that is published by Zoom itself. So that systems, that service, that video conferencing service that we are using right now, where it's published how many gigabytes per second are required for a single participant participating in a video conference, in a one-to-one video call, if they want to have high quality, HD quality, or HD with 1080p quality. And what Zoom publishes is the data rates, and for a different motivation, not for doing energy analysis, but for the reason of, do I have enough bandwidth for my Zoom call to actually work well? And going from that data, which supposedly should be fairly accurate, because if Zoom itself publishes wrong bandwidth consumption data, then the service will not work well. So it's in their best interest to have fairly accurate data. They don't want to over-claim, because that would mean that people would maybe shy away from the service if another one claims to use less bandwidth. They don't want to underclaim, because if people try to use it with insufficient bandwidth, it just won't work very well. So if we just use those numbers by Zoom and try to multiply, what does that translate to for a single 1 hour video call between two participants? We end up in, based on the quality level, somewhere between about 500 megabytes to 1.6 gigabytes. So not massive, right? How much is that if it's for a group video call? So for 1 hour participant, if we assume 5 to 6 people group participant call, we've got one stream outgoing, our own stream, one video stream. We've got multiple streams incoming. It does not scale perfectly with how many people are in the call, because there's only so many streams that you will actually see in parallel on your screen. But again, based on numbers that Zoom publishes, that's of course a little bit higher than with a one-to-one video calling, but not massively so. So for a 1 hour group call in HQ quality, how they call it, it's about 800 megabytes up to about 2.5 gigabytes when you go for the 1080p video calling quality. Now, if you try to scale that up, I mean, we don't quite have 1,000 students in here right now, but we can try to scale that to 1,000 participants, so from 6 people to 1,000, then we get to, for 1 hour, about 12 to 37 kilowatt hours if everybody has video sending enabled in a really group call. So please don't. If you're not actively participating from an energy perspective, it's actually much nicer to turn off your video streams. The social component is different. So depending on what meeting you have, other people might actually find it awkward if you turn off your video while they are talking. So that is, again, social norms versus energy consumption, not a very easy conversation to have. But just the energy perspective, only turn on those video streams that are currently active. So let's see, group call, 6 people, 1 hour, and estimate about 0.08 to 0.22 kilowatt hours. So depending on a lot of factors, the error bars are huge, but that's the order of magnitude of what we probably have in terms of real energy usage for just the data transfer. So this is really just a network transfer based on what it takes to get our bits across to another continent or just within the same country today, right now. The difference is not all that big. But we need additional services. It's not just a data transfer. It's not just that we all run the Zoom apps on our devices and they communicate with each other. We need additional devices on one side, which tends to have a big factor. So depending on, do you watch this on a 70-inch screen? Do you watch it on a laptop or do you watch it on a phone? There's a big difference in just the device energy consumption on your end or on my end. I'm having a slightly bigger one because I'm using our video streaming room, which of course is more than the phone, but that really depends a lot on the used device. If you also do the transfer not over wires, but through the mobile network, through a mobile network operator, then there is still a massive difference in the amount of energy consumed for that wireless transmission versus wired. So depending on technologies, it's probably a factor of round about 7 to 10, from 0.015 kilowatt hours per transferred gigabyte to 0.1 kilowatt hours per gigabyte. And that can, of course, go up even more if you have the high-speed transfer modes. But again, that's not all. We also need the cloud centers because the apps don't communicate directly with each other independently of the device, but they need some connectivity layer, which is really a data center that Zoom runs or that runs in different location in different hosting centers. And with the newest versions of Zoom clients, you can also enable that automated transcription of audio to text, speech to text transcription. And that at the moment uses large language models. We do not have any good numbers on what the energy impact of that is, but if everybody, if every meeting, if every single one-to-one Zoom call enables live language transcription, we can assume that the potential energy impact is large, though I don't have numbers for that at the moment. Now, let's put that all together. Let's put the data transfer together with the cloud efforts, with the energy consumption of our devices themselves. What do we end up with? Again, these are different sources for that analysis, but they do match up with the other sources of data that I had before, which makes me trust them slightly more. The numbers are not good. They're maybe orders of magnitude. But from those estimates of putting everything together, what we see is that a group video call with 5, 6 participants for 1 hour probably consumes about 0.1 kilowatt hours. On average, if people use a range of different device sizes, not everybody using those large TVs, also smaller devices, then this might be a good order of magnitude estimate. Is that much? We can compare that with about 1 kilometer with a battery electric car, or 5 times that with an internal combustion engine car. So you cannot go far with an individual car to save up on the energy effort of having a Zoom meeting through those means. Or put differently, instead of going somewhere physically from an energy perspective, it's a lot of saving, globally speaking, if we have video conferences instead of flying around the world or just taking our car into the next city to have those face-to-face meetings. We can reduce the data transfer even more significantly, up to 90% if we switch off video and go to audio only. So that old voice over IP call or just a phone call is probably a lot more energy efficient. And of course, you can go even deeper if you go to just textual communication, chat, or the old email. This is even more efficient, of course. Not though if that is intermixed with other media types. So if you, for every second chat message that you send, if you ask a generative AI model to generate a custom emoji with GIF animations on there, then the efficiency, of course, goes all the way down, and you will consume a lot of energy just for creating and transmitting that additional media. Okay, but can we trust that? So let's assume for the time being that we can be much more energy efficient if we use video conferencing compared to sitting in the same room or in the same conference hall, sitting in the same lecture theater and talking face to face. Can we trust that the communication that we are having is actually as secure, as private as it would be if we were sitting in the same room? And there, the quick answer is for text messages, audio messages, or if you use the right so-called end-to-end encrypted messaging client, messaging app, then yes, this is actually fairly secure. I'll come back to what I mean with fairly secure. Those end-to-end encrypted messengers, they exist. The top ones are Signal and Wire. Then we have the class of Threema, Matrix, WhatsApp, and then a couple others that claim to be end-to-end encrypted and are only partially so, Telegram, and a few others that do a good job usually of encrypting the content. Now, the content is one thing, and WhatsApp being one example there, you have to trust the proprietary app service provider to do a good job at implementing it. You can't check it yourself, and that they actually do what they claim that they do. Others like Signal or Wire are or Matrix are open source, and you can check those protocols yourself. And yes, in the crypto community, in the security community, we do that. And the consensus is that Signal and others are doing a good job. Now, what that means is that any law enforcement or anybody just sniffing your connection on the common Wi-Fi or your internet provider can no longer perform mass scanning. Nobody, if you use those messengers, can actually know what is being said and cannot really get into the content of any text messages or listen into video calls like we are having right now. But this is not all. It's not just about the content. All those messengers, they leak more or less metadata. What is metadata? Metadata is data about data. And when we talk about metadata for those end-to-end encrypted messengers, we primarily mean that social graph. Who do I communicate with? When do I do that? How often do I do that? How much do I communicate? Which media type do I communicate with those other people? Which groups do I belong to? All of that info is, of course, available to whoever runs that service. So that Meta in the current company name that used to be called Facebook, I think does not originally refer to metadata, but that is their core business model, collecting all this kind of metadata, even if services like WhatsApp actually encrypt the content that is transmitted through them. Signal, on the other hand, and Wire, to a very large extent, try very hard not to get and not to store any of that kind of metadata. So there is a big difference even between end-to-end encrypted messengers that all do encrypt the content on how they deal with metadata. Now, even the content encryption is not completely secure because there is a political discourse right now under the term of chat control of how much client-side scanning of content do we actually want to enforce. And our scientific position, and that has been the case for many years, that we've been saying kind of the same arguments again and again, is please don't do that. Do not try to break end-to-end encryption because if it's broken once, it's broken for everybody. And machine learning magic scanning of content enforced into the chat messengers does not really work. Lots of those arguments have been summarized. I'm not going through them again. And so far, the good news is we still assume that those messengers are actually okay. So to answer that question, can we trust that digital communication? I would say if you use the right software, yes, you can. You can for the content. You might need to be careful for the metadata. So if you care if anybody finds out that you have communicated with a separate with another person, then it's kind of hard to secure that. If your threat model includes the fact that you want to hide that communication happened at all, then maybe you should meet physically at a place that does not have any surveillance. If you don't care about this kind of metadata, then the content itself, yes, is secure. Next question. Digital communication requires that you know who is on the other side. So how do I know that this account that claims to be whoever, my friend Max, is really representing my friend Max? Because a profile picture is easily copied from any of the social media platforms. A new account with that name is very easily created. So how do I trust him? Is that by phone numbers? Um, Sneak peek, phone numbers are terrible identifiers for people. We just use them right now because for most of those messaging services, it's just the easiest thing that they can come up with. They don't have to care themselves about how that communication works, and they don't have to do the account management, but it's not a really good identifier. So what better could we do? We could use our digital identities that we already have. So in Austria, many of you might already have the digital driving license, which we prototyped quite a number of years ago. So this is an early prototype from 2017. Now, as of 2020, for example, in Android, we have what's called an identity credential framework where you can actually make those wallet apps. And by the end of 2026, next year, that's one of the other big discussions on the EU level, we actually should have a rollout of European digital identity wallets where nation state assigned identities can then be used to authenticate to each other, to physical persons on the other end, or to websites, and do so in a privacy conscious manner. What is the energy impact of doing that on smartphones? Very unclear. Probably not high, because a smartphone app that we can use to prove our digital identity to another user on the other end of, for example, that signal communication will not cause a lot of additional consumption, energy consumption on the smartphone. Probably measurable, but probably not significant whatsoever compared to a 1 hour phone call that we have. Now, that's on smartphones. What if those identities are not on everybody's smartphone, because that doesn't work in all use cases, but what if that is more integrated with the physical world? So how do we, for example, do that whole thing if we don't have a smartphone, if we have it on the cloud side, if we store our identities on the cloud side, and I use that, for example, because I step in front of a webcam and that identifies me, aligns with the account data that I have stored in the cloud, and then enables a verifier on the other end to recognize me, to recognize that, yes, I'm me, and this is on the other end, this is the account that I hold, and that's how I authenticate to somebody I communicate with on the other end. There are different ways to do that. So we can do that either with a central database where every individual has an entry in that central account, all the sensors, all the biometric authenticators, all the fingerprint sensors, all the cameras with face recognition, they all feed into the central database, and every verifier just knows to query that central database, and then you can easily authenticate people because I've stepped into this office. Anybody who is in this office must have this account, is me, and I can prove that to the other side. This is what, for example, India's Aadhaar identity system has been doing for a number of years right now. And there are other examples where this works. Or you could also say this is the Facebook account database that you have, where you can easily authenticate to that central database of accounts. And everybody knows how to authenticate with that if you want to log into a web page. And WhatsApp could use that database to align people who connect with each other. Now, what is the problem with this central point of view? All data that is being collected in a central place will most likely leak at some point. It's not so much a question of if, but more of when. You'll find the biggest names in this database. I like this webpage, it's being updated, and it just shows the publicly known biggest leaks of third-party data of people's personal data that they had on those accounts willingly or otherwise. And yeah, Facebook is multiple times in there, Microsoft as well, the big providers, Twitter, of course, they're all in there, as are some of the national providers. We have Aadhaar somewhere down here. I can't see it right now. I just updated this graph. It used to be somewhere in the middle here. So there are most of those big account databases have already had leaks. So there's an argument and we want to do it decentralized. That we want to have different providers for those decentralized account storages that we use to authenticate to secure our digital communication with. Now, that is maybe better from a security and privacy point of view, especially privacy point of view, because having all those account interactions in a single central database means that whoever runs that database knows exactly who is communicating with whom, can surveil that, and can also potentially censor it. What does it mean if a digital account is actually removed, is revoked from that database? You would be locked out of all this kind of digital communication. So a decentralized domain where we ourselves can decide where we want to keep our cloud hosted identities would be better from a security and privacy point of view. And that is actually like a small pointer to our primary scientific work. This is what we've been looking into for the last 5+ years, and we have some proposals there, how to do that on a global scale, how to do that privately, how to do that securely. Now, why did I talk about this here? Because it has an energy impact. Large data centers are much more energy efficient than very many small distributed ones, which is again a trade-off. If we want to avoid single points of failure, which are a bit of a problem from a security and privacy point of view, and we go to the decentralized distributed model, we pay for that with bigger effort, with maybe you could call it bigger waste of resources, of energy, and the actual hardware device resources, because we will need more devices. We cannot pack as densely as we can with highly centralized data centers. So that's a trade-off. That is a decision that we will at some point have to make when we talk about digital authentication, and the implication that we also need to know who we are talking to in the end, so that authentication, that identity infrastructure. There are more security issues we need to talk about. So supply chain security. It's not just that I need one service to communicate. That service needs other services, and those other services need other services. And even if we don't talk primarily about communication infrastructure, but stuff that is maybe more in the core concern of our power grid and electricity consumption, like charging infrastructure for electric cars, there are protocols where dependencies and chains of dependencies form, that one service needs other services, or it won't work. And those chains, sometimes also called supply chains or software supply chains, are another issue for security. I won't further deep dive into that, just pointing out that it's usually not just a single service that we need to keep running from an energy point of view, but we also need others that we not only have to keep running, but also others that we need to trust. And those supply chains, they are very much interdisciplinary. They are not just technical in the sense of, yes, I need those DNS servers, those time servers for my service to run. They're also organizational. Which other companies do I need to trust for the whole chain of services to hold? Somewhere in there is probably an AWS, an Amazon Web Service that at some point you need, or a Microsoft service that's one of your services then falls back to needing. And those are organizational dependencies, as we have seen in the current geopolitical situation where we have legal and regulatory concerns as well. If you have an account, an email account, or a video conferencing communications account with one provider in the US, and you are, for example, a judge in the International Court of Law, then maybe your accounts get terminated and you can no longer communicate. So those supply chains, they are not just technical dependency chains, but they're also very much organizational, economical, and legal. And our chains that we build for digital communication are getting bigger. And very often we don't even know what our dependencies are until they fail and we stop being able to communicate. So this kind of availability is another concern. We can save a lot of energy by moving to digital communication, but we might also get more dependencies than we actually know that we're having. And so with those additional dependencies, we might have less availability. The service might not be as stable as just driving somewhere and talking to people, and we need to be prepared for that. Okay, but coming back to the core of today, the energy consumption. Now, I hope that I've convinced you that we need good security in place if we want to trust our digital communication. So for digital communication to be able to save to actually save energy consumption by moving from physical to digital, we need security. But those security measures, they also need energy in turn. Again, a trade-off. If we want it to be secure, we probably have to spend something, and that something includes energy because we need things like runtime checks for our language runtimes. We need encryption and signatures. We need cryptography, which will probably rise in or likely increase in consumption with the move to post-quantum cryptography, which needs much bigger keys, much bigger signatures. So, of course, energy consumption will probably also rise. We need more complex public key infrastructures for software testing to not be completely insecure on the implementation side itself. We use fuzzing, we use other security testing. And yes, fuzzing on big code bases does actually cause significant and regular compute efforts because every update of that software package will probably run through the same fuzzing again to see if there are not any regressions or new bugs that are being introduced. Fuzzing is not to be underestimated in the energy consumption and should be considered one of the costs of adding security. I mean, otherwise the implementation would just be bad, and that's one of the best things that we can do. But it is an energy consumption that we need to add to the mix. Auto-updating software packages requires potentially large storage for the different versions of software packages. You multiply the version updates on every single client before it's actually being installed. The network transfer costs, all these are real costs of security measures. Or coming back to the technical supply chains, now it's kind of en vogue to have public ledgers, so-called transparency logs of these are the software packages that should exist. If you have a version that has been logged in this public log, then it's one that should exist and hasn't been tampered with and just sent to your device for an auto update. But all that requires, again, infrastructure and therefore energy. How much does security cause in terms of additional energy? See the talk by Daniel Cruz or some of his works in the past. He has got very interesting numbers for the hardware-based security. I tried to dig up some more recent numbers for programming languages because this is also what we are looking at the Institute. And it turns out if you want to save, for example, on the runtime verification, if you don't need a garbage collector, if you don't need a manual runtime, like Java and C# has, but instead if you code in statically compiled but type-safe languages that also give you memory safety guarantees, then, for example, you will see that Rust has an energy overhead on average in some of benchmark test cases of like a 3% compared to a C implementation, which is very often not safe or secure to use. It doesn't have memory safety. Java has an overhead of about a factor 2, C# already a factor 3 roughly, Go also roughly factor 3, and Python is very bad in terms of energy efficiency. Of course, those are benchmark cases, and those are just numbers that have been quoted a lot. So this study that has been done, I think about 3 years ago, has seen a lot of attention and has been cited very often. I've also found and put here as a link a critique to them, where I've read that just a couple of days ago. Some of the technical measurements were maybe not all that accurate, but the critique itself goes into some of the details of that analysis. And yes, some of those numbers might not be correct. They might still be correct within an order of magnitude, or maybe just within a factor or two or something. The tendency here that we see is still correct, though. So there are static memory safe languages that exist right now, and using them instead of something dynamically typed with a very fat runtime like Python or even just compared to Java can actually be good for memory saving, for energy savings, memory and energy savings. But today we're talking about energy savings. So one concrete proposal here or recommendation is if you want to care for security and energy efficiency at the same time, use a memory safe systems programming language statically compiled like Rust or maybe Go, depending on what you do. Java can be efficient if it's already hot. So for tools that are started very often and then end again, Java is very wasteful because it always needs to start the Java runtime. For some long-running server-side code, Java is not much worse than, let's say, Rust, for example, but it depends very much on the use case. However, globally speaking, choice of programming language does matter, specifically when we talk about secure code, when we really care also about the security of our implementations. Now, let's put this in contrast, assume video calling to other use cases that have often been quoted as well. It's very wasteful if you do that a lot. So how bad is Netflix video streaming? Why Netflix? Not maybe not because Netflix is necessarily the best, but it's been around for long and people have looked at the numbers. So there are very different estimates depending on which sources you look at. You've got two quoted sources here. There are more, but it's also somewhere in about that range that we had for Zoom, right? 0.9 kilowatt hours per gigabyte to 0.1 to 0.2 kilowatt hours. It depends very much on the video quality that you have. But if we assume, for example, here, depend on all the averages of video qualities, 0.077 kilowatt hours per hour of streamed video, then the rest of how much you really consume is not so much dependent on the streaming itself. The streaming has been made efficient, including the cloud. So those numbers, by the way, include the cloud storage backends that Netflix runs to deliver that stream to you. That's not just the network transfer cost, but really the what does it take to deliver that stream to your device. The rest is the device that you're using. And that is a big factor. If you watch that on a TV, you're somewhere between 50 to 200 or more watts. If you watch it on a desktop computer, it can maybe start with 50 watts, depending on the screen size that you have. Or if you've got a fat gaming machine, go up all the way to 500 plus 1,000 watts that the machine needs. Laptops, 500 to, yeah, gaming laptops. There's also hardly any upper limits. While a smartphone tops out at about 5 watts that it consumes. So that device that you use to watch that video stream matters much more than the actual live data transfer. Now, still, for audio streaming, those are much lower. For audio streaming, you hopefully don't do that on a 70-inch TV being turned on just to watch the audio, to listen to the audio stream. So for audio stream, when the device is less of a factor, then the actual radio power requirement does matter. So audio streaming, the recommendation from an energy point of view is have it cached. If that app that you use allows you to download music that you listen to very often and cache it on device and not stream it every time you listen to it, then this can save quite, globally speaking, that can actually save quite some energy for the transfer. Now, put this together. These are the numbers for Zoom. These are the put together numbers for Netflix streaming, and it's in the same order of magnitude. So somewhere between, if we assume very much average, also small video streams, 0.1 kilowatt hours for Zoom, we're in that range of 0.078 kilowatt hours to 0.8 kilowatt hours for an hour of Netflix streaming, where the biggest factor in that range is the device that you actually use for that. For smartphone viewing, most of the energy goes into the transmission if you transmit over the mobile network operator. Then that's the biggest factor and bigger than the actual display energy consumption. If you have a TV connected to a wired connection, it's very much the opposite. Now, one thing that needs to be mentioned, for most of the devices, at about 30% for TVs, 80% for smartphones, the energy effort goes into the production. So if you already watch video streams on your smartphones, then the best thing that you can do for energy saving is use your smartphone for as long as you can and not get a new smartphone every 1 or 2 years, because that's already most of the energy having gone into the device. Now, to round that out, we have video conferencing, we have video streaming as use cases. But let's look a little bit more globally. There are estimates, and again, quoted down here, there are estimates on how much our global internet network connectivity plus the data centers consume. Those numbers have been quoted by different sources, so at least the order of magnitude should be okay. And that mentions that we have about 200 terawatt hours per year for the large global data centers that run the Zoom services, that run the Netflix services, that run the Google and Microsoft and Amazon services. So all those big centralized data center services that you can think of, they used to fit in that about 200 terawatt hours. And then we have an additional about 250 terawatt hours for the network infrastructure, for keeping the internet running and being able to connect to those data centers. How much is that? Well, it's about 2% of the global consumption of energy, of electricity in this case. And how much is 2%? Aviation, the whole thing of flying around is measured or is estimated to be in the 2 to 3% of global energy consumption. Of course, there are many different effects. We have the CO2 emissions that are caused directly by those flights, which we don't necessarily have with data center if they're run with renewable energy, but it is not far off from the order of magnitude. Now, data centers have become very efficient. And by the way, those numbers, those 200 terawatt hours quoted here, they have actually remained interestingly stable over quite a number of years. Because yes, we consume more cloud resources, we consume more services, but because data centers are becoming more efficient, that somehow evens out. So those have been plateauing, those efforts for data centers, and have not risen significantly. The downside of having those highly densified and very integrated data centers is vendor lock-in. If you have one of those server farms, if you have one of those services that is really good at what they do, they probably are proprietary and you cannot easily transfer. So that's one concern. If you go to the highest density of providers, then you might actually be bound to their services and their APIs to use that, and it's hard to do. Now, there's at least 5 years ago, there has been a hype going around in that combination of security and what we're talking about today, energy efficiency. And of course, I'm talking about blockchains and cryptocurrencies. So can we use blockchains as a security measure to make our digital communication more secure? I won't go into the details about blockchains, but let's talk about the energy consumption, and it's bad. So if you look at the estimates done by the Cambridge University and being kept updated, we'll see error bars here and some estimates of somewhere between 100 and about 200 terawatt hours just for the Bitcoin blockchain with many different changes. So the average fat yellow line that you can see here, that has gone up and down, and that depends on lots of factors, like are the current miners in China? Are they being kicked out of China because they cause brownouts? They consume so much energy in the power grid that they actually cause the power grid to go down. They're being kicked out, and the number of miners goes down. So lots of fluctuations in there with events that you could name. But how much is that? 100 to 200 terawatt hours. If we compare that to countries, the upper bar, 200 terawatt hours, is just somewhere between, let's say, Egypt and Australia, the whole country's consumption. If you look at the lower bar, I mean, 100 or even lower, 80 terawatt hours, well, that's just a little bit more than Austria. So all the electricity that Austria consumes, including all the heating, including all the industrial production, including all the lights, now including all the electric cars, is a tad less than the lower bound estimate for just the Bitcoin cryptocurrency blockchain. And that does not include all the other blockchain cryptocurrencies that are out there. That's just Bitcoin, not the others. Now, how much value do we as citizens or people who live in Austria get out of Bitcoin compared to everything else that we use electricity for in Austria? I think that comparison speaks for itself. Now, people have claimed that, well, Bitcoin cryptocurrencies are good because they drive the construction of clean energy sources. And yeah, this hasn't been updated, but at least for the first 5 years of the hype cycle, we could see that. No, it really didn't. A lot of that was still coal, oil, and natural gas, and only a small part down here was actually renewable sources that went into Bitcoin mining. So, from an energy perspective, please do not blockchains as a security measure, at least not in this wasteful proof of work sense, because it really is extremely wasteful in terms of energy consumption. And let's not talk about NFTs. If you've heard about NFTs and are still interested in what they are, there's an excellent YouTube video that I'll link down here that you can actually watch, which can explain it densely and very to the point of what an NFT is. But I hear you say there are also blockchains that do not require proof of work. Yes, there are. There are blockchains that have proof of stake consensus mechanisms. The Ethereum blockchain has, for example, moved to that one, but we still have some assumptions. So questions. If you think of blockchain as a security mechanism, do you really need the irreversibility of all transactions? Or put differently, your developers do not make any mistakes, so you cannot easily correct a mistake if it's already been locked onto that temper evident, non-reversible, append-only ledger. Then do you really want to publish all the details of all your transactions? So coming back to the digital identity question, many people have suggested using blockchains for digital identity storage and use so that you don't actually have to trust a central provider with your digital passports or whatever to prove who are you. But then whenever you use that, it's on the public record, it's on the public ledger. Do you really want to publish all those details of when you use your elements that you have on the blockchain? Does really every node need to mirror the whole history? Just the Bitcoin blockchain, it consumes loads of storage because every full node has to mirror the complete transaction history since the beginning of the Bitcoin blockchain. Also not very efficient from an energy perspective. Or generally speaking, is there really nobody else you can trust? Is there no trusted third party that you can, at least for some assumptions of trust, use? There are much more efficient ways. The binary transparency locks, or generally transparency locks that I mentioned before, are also have some of those guarantees, append only public ledgers, but are so much more efficient. As soon as you start to trust one party just to keep the storage and update that chain, have a single storage of it, and then have other monitors that would catch it if it was misbehaving and was somehow changing the chain going backwards, then you can save all of those energy efforts and storage efforts that most of the blockchains, cryptocurrencies have. And how many transactions per second do you need? Because most of those blockchains are actually fairly slow and wouldn't even keep up with the web PKI system of X509 certificates, which does not use a cryptocurrency-based blockchain, but uses a transparency log for the efficiency reasons. And specifically for proof of stake, it's just a slightly different set of selectors. So it not whoever spends the most electricity gets to vote on what the new development for the chain is, but whoever has the most money in the system gets more voting power over the rules. So yes, it's energy efficient, but has other, again, social, legal implications that we may or may not want. So summarizing, there are many of those analyses. Mostly when people try to sell you a blockchain, luckily this has kind of stopped in the last 2 years, that people always push blockchain. This is most often not the correct solution to it, and it's definitely one of the most wasteful solutions that you can come up with if you think that is a security mechanism. Now, let's put that into our graph of how does that fit into those summary numbers. Well, if you compare an hour of Netflix streaming with about, depending on all the average device use, 0.1 to 1 kilowatt hours, let's assume the upper bound 1 kilowatt hours here, then this is less than 1/2000th of a single Bitcoin transaction. So if you do one Bitcoin transaction, if you speculate in Bitcoin, then don't feel bad about video streaming. You can watch 2000 hours of Netflix streams just for one single buy or sell transaction or transfer of whatever percentage of Bitcoin transactions that you do. Comparing this with the data centers, so Bitcoin has been estimated, just the Bitcoin blockchain, not the others, 100 to 200 terawatt hours. That is exactly that order of magnitude as we have it here with all big data centers together. So all the services that you get from Amazon, Facebook, Google, Oracle, whatnot, they all together consume about as much electricity as the Bitcoin blockchain. So from an energy waste point of view, please don't. Now, what about the newest hype, the one hype that came after Bitcoin? Generative AI, in the form mostly of large language models or multimodal, also picture generating models, etc. We don't have really good numbers. I tried to update my sources also just in the last couple of days, and I've added some new sources down here compared to last year. And it's really, really hard to come up with good numbers. There was an estimate from last year that actually used fairly sane methodology here that assumed that by 2026, data centers might actually go up to 600 to 1000 terawatt hours. So what I said before, that data center energy consumption had been plateauing somewhat because yes, we used them more, but they also became more efficient. Now, because of generative AI, is completely going out the window, that assumption. So generative AI, current energy consumption, training plus inference, is massively increasing the energy effort that we put into data centers. There are also some, the last line down here, there are some sources that mention that it might actually plateau because there's a lot of energy savings that can be applied to the current large language models. And if everybody applied those savings, then the increased usage of large language models would somehow compensate with the increased efficiency. I can only refer you to those two that I found that seem to be fairly well thought out and fairly sane. But I think it's too early to tell. We don't really have the historic numbers like we have, for example, for the Bitcoin estimate of energy consumption. We don't have that yet. And so we need to watch it. But it is, globally speaking, the energy effort going into generative AI is concerning. And we definitely need to watch that one because that might actually outweigh all the other numbers put together. So trying to come to an end, to summarize, how good are the numbers that I've shown you today? And I don't know. I don't even know what the error bars are. Those are very first rough estimates that I've tried to collect from many different sources, and I cannot, scientifically speaking, tell you how good those numbers are. The honest assumption is they're probably not very good. So let's look at the network transfer consumption, just doing those multiplications and having a metric like kilowatt hours per gigabytes is obviously wrong, specifically when you extrapolate it, because there is a very significant base level of electricity that we need to just keep the equipment running completely independently. If we transfer any bits over our copper wire or fiber wire, it needs electricity to keep both sides of it running, to keep the maybe amplifiers in the middle of fiber cables to keep that running, and that is significant. And that base level does not depend on how much we actually transfer. So this kilowatt hours per gigabyte can best be used for attributing past usage, but for extrapolating to other use cases, it's very hard to do that. For data centers, it might be even worse because we have even less direct data. Very often, those estimates from those numbers that I quoted, they're based on indirect data. So, for example, how much a company reported in its last financial report of what was the cost of running its data center, and then figuring out what electricity consumption that cost might translate to, what hardware cost that might translate to. And also, it's not comprehensive across the world. So, very often, those global data points are extrapolated from very few actual data points. So you might have an idea of how much electricity some data centers by some companies consume because they might be more transparent with their data. And then people extrapolate to the overall global consumption. And that's obviously not a correct number. It's at best an order of magnitude figure. And it's also changing rapidly. Now more so than ever because of that AI hype, generative AI hype, those numbers are changing really rapidly. And previously, previous predictions, also self-predictions of companies when they would go to 100% renewable energy, have now been kind of rescinded and are no longer plan of record of going fully renewable by most of those data center providers because the energy effort has gone up so significantly. Client device usage, again, depends on so many things. How often does the app actually transfer data versus just use cache data that it had in storage? How much does it go into standby saving modes? For example, if you do audio streaming versus keeping the screen all the time, how often do you charge? Um, Increased efficiency on devices is often counteracted by then them being used more. So if you get a device that's more energy efficient that would actually last for 2 days in your smartphone usage instead of the day before, you might use it more because now you have the battery power to spare. So all those estimates are really, really hard, and therefore please take all the numbers from today with a big grain of salt and maybe use them only as guidance of what we should be looking at and maybe just for comparing them to each other, but not as absolute numbers that you would then use to optimize any kind of usage for. With that, thanks a lot for your attention. And do you have any questions besides should I use a blockchain? Thanks so much.
Thank you very much for the presentation, for the very honest presentation, also concerning the energy numbers. As I take the icebreaking question, you were talking about these identity frameworks. Rene, what about ID Austria?
That's a good one. So ID Austria, from an energy perspective, I believe is not bad because the ID Austria, as we have it right now, holds most of the signing keys in a central data store. As far as I've been informed, Bundesrechenzentrum actually runs that with reasonable security. I haven't heard of any leaks so far. From a security point of view, I don't love it that we have all the private keys in one big store instead of having it directly distributed to people, but I get the practicalities of it. When it was based on smart cards and smart card readers that you had to buy, nobody used it. Now it's based on smartphones. Standard smartphones, we don't trust with actually keeping your signing key as secure that you would use it as a qualified signature. So it's a trade-off. But from an energy perspective, I think not a bad one. Austria is within the European countries probably among the most well prepared to roll out that European digital identity wallet in the EU. We've had the driving license, the Austrian driving license, in an unfortunately Austrian only so far. It is really mostly following the ISO standard that we have helped write as an institute, but with a small twist because there's some legal ministry internal snags where it's not completely standards compliant, but we've had it. So we've had those things, and what you need from the energy point of view is smartphones that people have already. The additional energy cost on smartphones for having those wallet apps on there is negligible. I don't think we could really measure that. The energy cost for running that signature service that ID Austria currently depends upon is probably also in the measurement noise when you consider most of the other streaming services. So I would consider that not to be too much of an issue. It can be a big bonus when we can have good confidence that we are talking to the other person on the other side. So if Zoom integrated, for example, a login with an ID Austria, I think that would actually be a good thing. It might not be in Zoom's interest because for the time being, they can monetize better if they have their own accounts. But yeah, um, just neutrally speaking, we should like it if that integration happens.
So you mean, so what you say is that we are kind of not so badly prepared for this European identity framework.
I would say so. I'm still not sure if end of next year we will actually have an Austrian national wallet that will be fully spec compliant. We're still writing some of the specifications as we speak. They're not
Okay.
final. Some of the nuances, like how to deal with pseudonyms. Can you use a pseudonym name to register to a web page? How exactly is that handled cryptographically? That is not yet even fully agreed upon. So that's why the deadline end of 26 is tight. I think it would really help the trustworthiness of digital communication if we had such a service across the European Union. And the EIDAS Regulation 2.0, which is the basis for what should become the European Digital Identity Wallet, that explicitly is meant to open those identity services from just e-government to arbitrary third-party services. So it would be absolutely positive if whatever, Zoom or the other communication services, maybe Signal, maybe WhatsApp, would actually allow users to use that kind of identity to prove that you're talking to the right other party.
There was a question, but about how to, examination, and this has been answered by Marianne. Thank you in the chat. Since there is no other, or so far no other question, I would have a follow-up question concerning. It goes further in this on identity issue. I mean, there is this discussion on also proving your age via identity. Yeah, especially all this I say bad content
Yes.
on the social media. To which extent, what is your kind of your stake on that, or how do you think
Yeah,
where
that's
we
a very
are?
hard discussion. From a security point of view, we have good ideas on how to do age verification, cryptographically speaking, without leaking any other data. So even with that mobile driving license standard, that was one of the use cases that we've been discussing since about 2018, beginning of those standardization discussions. And we can make that happen. So we can reasonably prove our age without revealing any real form of ID, without revealing any real name or any citizen number or something, just that, yes, over 18 is there. So if implemented correctly, and the discussions on the European Commission side for that go in a good direction, we might actually, for the first time ever, get some official national services that use zero knowledge proofs. So very fancy, very advanced crypto, we might actually get in. Discussion is still happening, but I'm remaining positive that we can actually do this in a privacy positive way. But there's the other part, and that's what civil rights organizations are, I think, correctly concerned about. It becomes a bit exclusionary. What if you don't have a smartphone that is capable of that? What if you don't have a European digital identity because that's for European citizens? What if you're not a European citizen but want to use services here or live here and you can't get the full ID? Are you excluded from proving your age that way? Do you then need to whatever upload the photo page, the scanned photo page of your passport to use that same account? Because you're not in that in group of you have the full privacy first positive digital identity. That is, I think, a hard question, and that has not come up enough in the public debate. There is a
Alejandra
raised hand, I think.
Ventura raised the
Yeah.
next.
Yeah, hi Rene. Thank you for the insightful talk. With all this information, actually, there is a point that comes to my mind very inevitably. How does this all equate then with the, like nuclear power generation? Because of all the distribution of how you showed, that the current energy consumption is, and what's your take on that? I think that's probably very, I don't know, like interesting to know what your perspective in that.
I'm sorry, I lost you for about 10 seconds in the audio signal. Could you repeat the core of your question, please?
Yes, how does the nuclear power generation equate in all the distribution of the power consumption, and what's your take on that?
Okay, thank you. Yeah, a very good one and a very hard one. I am very ambivalent about nuclear power consumption, to be quite honest, because it is a source of power that does not massively contribute to the CO2 emission right now. CO2 emissions are probably our biggest issue from a climate change perspective at this point, CO2 and methane. We can create electricity through nuclear power generators that are probably not CO2 neutral once they've been produced, massive amounts of cement, etc., but that can keep on running without contributing a lot to current warming. The problem of what to do with nuclear waste is currently still unsolved. Now, was it wise of Germany to turn off working nuclear power plants? maybe not. The same thing as a lot of the effort has gone into the construction that's true for our devices that we use for digital communication was a lot more true for those nuclear power reactors. So keeping them running while they're still safe to run would probably have made Europe's energy mix better right now. Now, constructing completely new nuclear power plants, as some of the data center providers are currently actively planning to do because they've got massive energy needs that their power grids, wherever they run, mostly in the US, cannot meet. Constructing completely new, small, and kind of untested designs of nuclear power reactors might also not be a good idea. So this is a really hard one. It yeah, I I actually don't know what to say. I'm kind of happy that Austria does not have nuclear power at the moment. I'm still on that side of the fence. But if we had it running, I may not have voted for turning it off prematurely while we have other transitionary problems. A very good question, and maybe one for political debate more than for the actual numbers. Now I see there's a question in chat, right? What do we do when our digital identities are stolen? Ah, yes, we get screwed because when somebody can take over your digital identity and sign in your name and make that count as a written signature, that's very bad. And we'll have to figure out how to revoke that digital identity. So most of the schemes that we discuss need to deal with the case of how do we revoke digital identities. And that's not an easy answer. For a driving license, what does revoking mean? If the police revokes your driving license, then they care about you not being able to drive a car the next day when you get into another traffic check, that it counts as revoked. So they will have to figure out how to put your driving license on their own list of revoked licenses so that they can change that. What does it mean if your phone gets stolen and somebody knows your unlock PIN and can then use that identity? You might need to have this revoked much quicker and much wider than just telling the police about that. So you might have to very quickly, anybody who might verify that ID needs to maybe know within minutes that this should no longer be accepted. Then the privacy part comes in. So we know roughly on a technical level, we know roughly how to do these online revocation schemes. On the web system, that would be called the OCSP as one protocol that we can use for online revocation checking. Now, do you want that for digital IDs? Because what does it mean? If you do an online revocation check every time your ID is used, it means that everyone verifying your ID needs to query that probably centralized revocation service if that's still active or not. That revocation service does not learn maybe what you exactly use your ID for or what you communicate with on the other side, but they learn that you use your ID with that one verifier, with that other party, because they just queried that revocation service on the other end if it's still active or not. So you leak metadata through such an online quick revocation check. And for some use cases, that might actually be bad. So this is again an extremely interesting question. I love those today because that's another one that I don't have a good answer for. It's a bad problem if the digital identities are stolen. The easy answer is, well, you just revoke it and tell the world that this should no longer be accepted. The hard part is how to make that happen if devices are occasionally also offline, if not everybody has constant internet access all the time, and without leaking potential privacy relevant data in the process. There are concepts, and I could probably talk for an hour on what we have tried and what can work in some use cases. So there are ideas, but there's no single textbook answer that would work in all the use cases.
Thank you for your answers. So you see at least that your presentation has sparked a lot of not so easy questions.
Yeah,
less easy answers.
Those are the best questions, the hard ones, because as students, please look into those questions. We will need to solve them. They're all excellent questions. If you're looking for research topics, there you have some. Open questions are what science is about.
So this is a very nice last statement for the presentation. I would like to thank you, René, for the excellent presentation. I thank the participants for, continuing thinking and discussing further issues. We will continue on that also next week. And thank you to all of you for participating in this online public lecture series.
Thank you, and have a
Bye-bye.
nice evening, everybody.